Welcome everybody to today's talk with the Design Plus Plus speaker series provided to you by the Design Plus Plus initiative at ETH Zurich. My name is Michael Kraus and I'm happy to be your host today. It is my special pleasure to also welcome our guest and lecturer, Professor Miller, who is joining us from Singapore today. Before I introduce you to our speaker and the talk, let me shortly provide some background information on our new YouTube channel of the speaker series, where you can all find the videos under this link here. The Design Plus Plus speaker series is a recurring event where we will provide invitations to upcoming events in due time via email, our homepage, or the YouTube channel. At the moment, there is a number of professors from the departments of architecture, civil engineering, and computer sciences of ETH Zurich involved in the Design Plus Plus initiative. For the running business, there is 3 leading postdocs responsible, which you can see here. And another postdoc will join us now in December for our team and supports us here. So in case you're interested in the future of connecting AI, machine learning, or extended realities in the AEC industry, just reach out to either of us, and we would be more than happy to discuss any projects or ideas with you in the further. Having said that, on the background of the Design Plus Plus initiative and our speaker series, now let me introduce to you our speaker of today, Professor Dr. Clayton Miller, who is joining us from the National University of Singapore today. Dr. Miller is an assistant professor at the National University of Singapore in the Building and Urban Data Science Lab. He is a former Ph.D. fellow at the Institute of Technology in Architecture and holds a Doctor of Science from ETH. He also holds a Master of Building Sciences from the National University in Singapore and a Master of Architectural Engineering from the University of Nebraska in Lincoln. He is a former CTO of Optiras Pte, a Singapore-funded startup, and a former Fulbright Scholar to Singapore. Please also have a look at his papers and especially his homepage, which I linked here. All that background information on this talk and our speaker is also linked on the YouTube channel under the video, and you will find more information there. Having said that, it is a great pleasure to hand over the stage to our presenter of today.
Great. Thank you so much, Michael. Thank you for the invitation. I like smaller groups. Like I said, I think it's nice to have a conversational aspect to the Q&A later. I'll go through, I've got way more slides than I need. I think I'll try to go through them as quickly as possible to give us about 10 or 15 minutes at the end for Q&A. First of all, apologize. After sending over the title of this talk, I realized that it's absurdly long. This is the only time I've given a talk. I promise this is the only time I've given the talk with this long of a title. Really what I want to do today is kind of cover, take a step back and look at the community, look at the field of architecture engineering, and look at the field of data science and machine learning, and try to figure out or show how I've tried to figure out ways of converging these two different communities in a sense, in terms of people and skills and teaching and research and techniques. I do know that Design Plus Plus, the group that you all have at the ETH is really kind of diving deeply into the design process of buildings and infrastructure and things like that, and using AI. So today I'm planning to take us kind of a step back with us and try to give you all the experiences that I've had in the more general field. So you can scan this QR code or go to this bit.ly to download the slides that I'm going to show today, because like I said, I'm probably going to go through them a little bit quickly, so that but if you have, like, you want to look back at the slides, you can do that. So about me, I mentioned before, well, I haven't mentioned to everyone yet, but I am American. I'm from the University of Nebraska, and I moved to Singapore over 10 years ago to do a Fulbright grant and do a startup. But like was mentioned, I came to Zurich in 2012 and spent part of my time between Singapore and Zurich, between the Future Cities Lab and the ITA, the Institute of Technology and Architecture. and then made my way back to Singapore about 4 years ago as a faculty member here at the National University of Singapore. So to just give you a little bit of a context, and my background really is in mechanical engineering or architectural engineering, but immersed in both the data science and the architecture side off and on throughout this journey. The group that I have here in Singapore, we call ourselves the Building and Urban Data Science Lab, and I'll show two projects today, or 2 or 3 projects today. Really, it's kind of the overview of the 3 projects that really try to converge data science and building science. My group focuses a lot on the operation side of building. So we're looking at the energy consumption or the measured energy or the IoT sensors that are deployed across buildings. In addition to human generated data, actual humans in buildings, occupants as they're called, and the data that they create. We collaborate with other groups that do focus on design phase work in terms of energy modeling, but also generative design and the types of things that are probably focused on quite a bit by this community. And we think that actually it's the whole life cycle of the building, that the data being generated in all the life cycle components is really necessary to create a good building and to operate a good building. Those of you that are not familiar with my department, it's called the Department of Building. We're kind of the sister department to the Department of Architecture here at NUS in what's called the School of Design and Environment. But also we're part of what's called the Institute of Data Science that's been developed or started here in Singapore as a cluster of the different disciplines across the university, and a place that all of us can get together and interact and learn from each other in the context of data science and machine learning and things like that. So those are kind of the foundations by which we do research here in my group. So this is a couple slides these are a couple of slides that I put at the beginning of a lot of my presentations. It's all about the construction industry in general, and how we fail to achieve economies of scale. Like the title of this Economist article that came out a few years ago is really that efficiency eludes our industry. And there's various reasons that are brought up in this article, which I think are really interesting to read. But this is a graphic here on the left that really shows the divergence of other fields such as manufacturing and retail and things like that have used technology to increase their productivity, whereas the construction industry has actually, there's a negative correlation to productivity when it comes to technology. And this is a kind of a funny quote from an architect who says that, everyone else is using iPhones, we're still in the Walkman phase. So the question that I really asked myself in the last 7 or 8 years, even since I started at the ETH and the Institute, was how can we use machine learning to transform our industry in ways that increase the capability of what we do as professionals in this industry, while reducing the amount of time or the manpower that it takes, but increasing skills and decreasing time that it takes to build, design, build, and operate buildings. And so this has happened in all those other industries. Why not our industry? And this is a slide I throw in there for audiences that are unfamiliar with the basics of machine learning. This really sets the foundation for the first project that I'll talk about, which is the machine learning competition that we hosted last year. So you have 2 types of learning, unsupervised and supervised learning. Those of you that are deeply into using machine learning for your applications know that there's kind of a combination of using these techniques in certain workflows that provide the most value. And both of these processes have really influenced the way things are done in other industries. So one of the things that we've done in the last few years is we looked at one example of machine learning in the context of operating buildings, which is predicting energy. And this is a visualization of what's called the measurement and verification process. So you have energy being consumed in a building, and then at some point you want to incorporate a change in that building. You want to renovate the building or improve the systems or make even just operational changes. And at that point, you want to predict what building would have used without that intervention and compare it to what it did use after that intervention. So the green, basically the green line versus the blue line here on the right side of this graph. So this is the calculation of energy savings, which allow people to gauge how successful an energy savings implementation measure was. In this field, this particular vertical of machine learning in the building industry, that we did an analysis of one of the big reviews about this field, and we found that machine learning is applied usually on a case-by-case basis. In the building industry, we're very focused on case studies. And so whenever you find research literature, it's generally machine learning applied to a single building. And that's the case with energy prediction using meter data. So, you know, this leads to a situation like what you see here. You have a certain model or algorithm or process, you have a case study and you have a researcher, and you apply that to that case study, you apply that process to that single case study. And of course, everybody comes out the other end of this process saying, like, I found a really great machine learning process. It's fast, easy, accurate, blah, 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 all these different things. But the problem with that is that when you look at least from the energy perspective, you're not testing how robust that technique is or that algorithm is across the building stock in general. And this is one of the key parts of machine learning in other disciplines, is that there's a constant effort to try to make machine learning as quote unquote generalizable as possible or as robust as possible in its application to whatever it is you're trying to predict. So this is something we wanted to focus on. Like, how can we create a situation where you have a large data set of lots and lots of buildings, you have an objective, and you're getting people to basically apply their techniques to a large group of buildings. And then at the end of that process, you can basically say for sure that a certain process is faster than its peers, it's more accurate, it's easier to implement than its peers. These are all things that you can do if you have this type of structure, which is not very common in our field. So the mission behind this, you know, this scenario was to try to figure out how we can use machine learning in a more scalable and generalizable way, and teach industry professionals to use these type of models within this field. So this is really where I get into the first type of project that I want to talk about today, which is, well, before I get into that, the first thing we did before the competition is we created an open data set as a sort of a catalyst for the community to start to learn about how to apply machine learning to this particular context. So the Building Data Genome Project was released in 2017, about 4 years ago almost, as an open data set which people can apply their techniques to, and they can compare apples to apples comparisons between techniques. This basically led into, in 2019, we were able to, I was leading a team of about, there's about 10 people from around the world that we got together and we found data sets from all across the world, and we sort of combined all of them and created a context which we then put on the Kaggle platform, which is an energy predictor competition. And those of you some of you in the audience might be familiar with ASHRAE, which is a big organization that focuses on energy and air conditioning and heating and systems in general. And they had actually machine learning competitions that they hosted in the early 90s. So there's actually a Great Energy Predictor 1 and 2 competition in 1993 and 1995, something like that, where machine learning was, in fact, maybe you aren't familiar, but machine learning has actually gone through different sort of waves of effort. And if anyone's doing research in the 90s, you know that machine learning had that first wave. And so there was a predictor competition in the 90s that we sort of modernized by creating a super large data set for this particular context, over 3,000 meters from about 1,500 buildings. And I would highly recommend, I'm not going to go into like all the details of this competition, just kind of the results. But if you go to the link, or if you go to Kaggle in general, you'll see you can find our competition through Googling it. But when you go to Kaggle, you'll also see that there are dozens of other competitions. And if you're not familiar with Kaggle, I highly recommend that you go through and look at some of these competitions, because they come from all different industries and different types of applications, different types of data, different types of machine learning objectives, whether it be time series data prediction, which was the case for our competition. You also have lots and lots of image based competitions, sound, text, natural language processing competitions, and even now Kaggle has a platform now where you can actually have competitions related to simulation or emulation, and which is really interesting. So please check out Kaggle. You'll get kind of a crash course in Kaggle through the next few slides, but it is, I would say, one of the best resources to understand this concept of generalizability and robust testing of models, which is really the whole point of all of these competitions, is that you're given a large data set, training data set, you're given an objective to predict or classify or various things, and you're competing against thousands of other people to create the best technique according to a certain metric. And so you'll see, anyway, I'll get into the details now so you can see in the context of our competition how that kind of worked. This is kind of the details of the objectives. The blue areas, this is to represent the data sets that were given to the contestants. They were given a year of training data from meter data from all around the world. They were given weather data as well. And they were asked to predict these other two colored sets, the orange data set and the red data set here. So the orange data set was data that was used to predict what's called or to create what's called the public leaderboard. So people would actually use the training data to create models, they would then make predictions. They would upload those predictions to the Kaggle platform, and they would get an instantaneous score to see how well they did against their peers, according to how accurate their model is. And then the red data set was actually a holdout data set that wasn't scored until after the competition was completed, fully completed. And that was actually the data set which determined the winners of the competition. And the winners actually received, there was a breakdown of the top 5 winners which split $25,000 US dollar prize money pool, which was supported by ASHRAE. So like I mentioned, yeah, here this is kind of the structure of that. They download the data, they create the models, they do the predictions, and then they upload their submission, and then they get on the leaderboard. And they can make submissions twice a day for the full duration of the competition. Our competition was about a little over 60 days, so a little over 2 months. And so people could actually improve their models and update and upgrade their models based on seeing how different tweaking and tuning of the models actually helped improve the model over time. And overall, it was really successful in terms of getting lots and lots of people from around the world to look at this particular context. So we had about over 4,000 participants. The participants could join into teams. They could create teams of up to 5 people. And we had over 3,600 teams from all around the world. The biggest representations coming from Japan, China, Russia, United States, and India. And over the course of the competition over 2 months, those teams submitted almost 40,000 total solution predictions. And they were basically competing against each other the entire time to see who could come up with the best model or prediction. So beyond the top 5 winners, there were also quite a bit of what we call notebooks that were created in this process. So maybe some of you who are learning or already use Python or R are familiar with Jupyter notebooks, which you can find all over the internet. If any application that you want to try to tackle using Python or R, you can generally Google whatever that is, and you'll probably be able to find a Jupyter notebook, which gives examples of how to do that. So in our context, and Kaggle has something similar to a Jupyter notebook called a Kaggle notebook, basically the same thing. In fact, it's probably based on the Jupyter project. So in this competition, we had over 450 of these notebooks being shared by the audience, by the participants, which broke down according to the categories that you can see in these two graphics, with a big chunk of in fact, the most popular type of workflow being submitted being what's called starter code or beginner code. And these are solutions or workflows that allow people to see an example of how to start out with a raw data set, how to clean that data set, how to process it, how to start building models, how to create what's called ensembles of models, how to post-process data. All of these things are, we created this big crowdsourced set of content that now people are coming in and learning from and cloning these notebooks and using them to get started with this particular context. Overall, I would say that this is the biggest output of this competition, was all of the crowdsourced generated content towards this particular application that are out there that people can really learn from. And of course, the top 5 models, which you can see the final private leaderboard or dashboard, these are the top 5 winning teams. Some of them had, the top team had 2 people in it. Second place team had 4 people. And these top 5 teams were given prize money, but they were also required, in order to get the prize money, required to open source their solutions, to explain their solutions. They created 20-minute videos which explained how they made their solutions. They explained the mentality behind their workflow. And it was really fascinating because it turned out that in this particular machine learning application, it wasn't so much about the models as it was about the pre-processing of the data. So in this application of predicting energy, removing outliers, removing like weird behavior from the training data, which is probably not likely to occur in the test data, turned out to be the differentiating factor between the top 5 teams and, let's say, the top 25 or 30 teams, or even the top 100 teams. So it was eye-opening. The other thing that we learned was that neural networks or deep learning models were not the most popular model. They didn't perform the best. In fact, tree-based models, gradient boosting tree models, tree-based models were the best. And specifically, there were certain packages such as LightGBM and XGBoost, which performed the best in this particular data set. And this is really, I think, worth emphasizing, that this was such a key output, was that every application of machine learning is slightly different. Every domain is different. So there are different tools in your toolkit which you can apply to it. And there is no just one size fits all tool like deep learning that you can just throw into an application. So this was really interesting for the community. There's a lot of people now using this, the results of this, to relook, to sort of look at the models that we use in the measurement verification field in more detail and how they can be basically improved. And M&V, it's one thing that, if you're not from that field, one of the things that's really disrupted measurement verification as a field has been the COVID pandemic. So the year 2020, the energy consumption in buildings looks nothing like any previous year in history, because we haven't had a pandemic. We haven't had a global pandemic in the last almost 100 years. So that's where a lot of these innovations in modeling can come from, is how to create models. What is the right training data for models? So 2020 data will not predict 2021 data, for example, in this particular context. So like, that's where when it comes to machine learning, that's really where a lot of these skills have to come into play, learning these skills, and Kaggle is a great place to do that. So I want to kind of pivot away from energy. Let me talk about the other part of the operations side of buildings, which are occupants. We also look at the age-old question in the built environment. What do occupants want? What makes them feel satisfied in terms of thermal comfort specifically? So this is another type of project that I'd like to talk about, because it shows an example of not just like modeling data, but creating data in our context. If any of you are familiar with the thermal comfort evaluation community, this won't be a surprise to you. This slide is from a study that was released last year, looking at over 40,000 data points from dozens of studies around the world that show essentially that our traditional way of predicting thermal comfort is not accurate. Our models are only about 33 to 34% accurate in predicting if a person feels hot or cold or somewhere in between, based on the conditions of that room, based on the clothing the person's wearing, based on their metabolism, all the things that you would think are variables that would accurately predict thermal comfort, they just don't happen. They don't work that often, or they don't work the majority of the time. So people have been thinking, oh, well, what are some of the other data that we can throw into those models? Well, we could look at gender or age differences. And this is a visualization of a couple studies that try to show whether these two variables are significant or insignificant for thermal comfort. And there's no consensus. That's the result. If you can see that significant versus insignificant versus somewhere in between is basically kind of split across all these studies for both gender and age. So as data scientists, what else can we do? You know, should we measure every single factor that influences people's comfort in buildings? So this is a visualization that we created to try to aggregate all the different things that can influence people's thermal, visual, and oral comfort, or noise comfort. And there's tons of these things. There's dozens of things that we can measure very easily, things that we can't measure very easily. So the question we ask ourselves is, how can we use data science or machine learning to mitigate the need to really measure all of these things? So we draw a correlation to other disciplines once again. So marketing and advertising, you have a product and you want to optimize the process of people trying to buy that product. So, you know, one thing that you could do, traditionally one thing that they would do is do demographic surveys. They would observe people's spending habits. They would even use IoT to measure why people, or target people to buy a product. But the thing that we all know that has happened in the last 10 years is the ability to collect information about people's preferences from social media. So creating ways that people can express something that they like or dislike using star ratings or like buttons or things like that. And then using those data to understand what a person might be most likely to buy. So in the built environment, we don't have products. We have spaces. Spaces are our product. So in the building industry, we have correlations, but we have post-occupancy surveys. We can detect occupants. We can use IoT and things like that to predict what people want. But the thing that we're missing for buildings in the operations phase is really like a like button or something similar to social media, where we can collect information about what people like in a sort of passive way. That's not a complaint. It's really just a sort of a tag that a person would give to a space to indicate that they like that space according to whatever your objective is, whether it's thermal comfort or even privacy or things like that. How do we make a like button for spaces? So this is not for data science, this is not a modeling problem. This is a data creation problem. How can we get an alternate set of data which can improve our models, our traditional models? And so we created a project. This is a project in collaboration with UC Berkeley's Center for the Built Environment. It's a Fitbit smartwatch-based platform called Cozy, and it's an open source project that's community-driven at this point, from various entities around the world that are using smartwatches to collect information from occupants about what they like and what they don't like. And this is a method called ecological momentary assessment method, which has been used quite a bit in psychology, medicine, and marketing, where you are finding information, you're sort of trying to get people to give information where they are in the real world when they feel that whatever you're trying to ask them a question about. It's real time, and it's self-reported, repeated, and intensively longitudinal. So that's where the EMA part comes from. Ecological momentary assessment acronym comes from, which is what this project is about. And so Cozy as a platform, we've gotten a few different rounds of data creation. The first one was only about 15 people, which we deployed around Singapore. We basically gave them a watch and we said, wear this watch, and whenever it sort of vibrates or prompts you to give feedback, just answer the questions on the watch. And so here, this first deployment was just meant to show that these data could be created in a scalable way. And then the next experiment, what we did was we wanted to expand the number of people. We got up to 30 people this time. And we also expanded the ways that we converge data from different sources. So we have data from the smartwatch. We have data from what's called a Bluetooth localization system, which can tell where the person is. We had sensors on the person, and we had all of these things flowing into the smartphone of the participant and then into the cloud. The key with this, and this is something that is another lesson learned, which is more generic, which I think a lot of people within this group could also relate to, is that data science is often, or machine learning in this context is often coming from different data sources. So in the design phase, you may have, you're using different tools. You might be using Revit or Rhino, Grasshopper. You might have energy models. You might have different types of data flowing from different places. And you also have the human being. So of course, in design, you're always going to have that human in the loop that needs to be a part of that process. So that's really the tricky part. It's like, once again, it's not about the models. It's not about some magic model you dump data in, you get inside out from, you get the results from. It's about the convergence of the data that comes in and making sure that basically the human is part of that process. So this is a little more about that second experiment we did. Here you can see the 3 questions that we asked people. We asked them if they prefer it warm or cooler, or they're comfortable, dimmer, brighter, or comfortable, or quieter, louder, or comfy. And the results of that really, here you can see kind of a BIM model representation of the points that we collected from all of the people. And then below you can see the different sensors that we had deployed in the building to be able to converge the different types of data amongst these, from these different data sources. And then the modeling part, which I didn't show here, is based on how do we take all these data and then convert them into insight? How can we use those data to either control the building, to control the systems in a better way, or to understand which are the zones that people like the most and which are the zones that people that we need to basically come in and improve something to make more people happy. But also we're looking at not just changing spaces, but also changing people's decision-making processes. So we're also looking at ways to nudge people based on the feedback that they've given over the course of the experiment. What are the spaces that they specifically like, and how can we give them the ability to choose those spaces as opposed to other spaces that they may not like? So that's a project called Space Match, which I didn't include here, but you can check out as well if you check out our website. So once again, Cozy is open source, so please go to the website to check it out if you're interested. I know a lot of you are on the design side, so maybe this is not as interesting. Maybe it is interesting. Maybe this is something that the type of data being generated here could be a feedback loop to the design phase, potentially. But check it out nonetheless if you're interested. And then also just know that we have another platform on the Apple Watch that we're developing, which has a lot of advantages in terms of creating kind of more of a chatbot style interaction between the occupants and the platform. So both of these are really exciting projects that, once again, on the operations side. So last thing I want to talk about, and I think I'll try to zoom through this. The message is very simple. It's that models, data collection, all these things are great, but we get nowhere without the right skills. So I've done a lot of discussions with a lot of people. That's what this slide shows, a lot of logos there, including the ETH Zurich, where I've talked to people and I've worked with data sets from buildings. And the feedback that I always get is no one uses the data in reality. So all of us in research, of course, we use tons of data. We build tons of cool models. But in industry, you don't see people using data quite so often. It's becoming more common, but it's not pervasive yet. And the feedback that I always get also from talking to people is that it's the skills of people in the industry. Finding people who can use tools besides just spreadsheets or Excel. People might say, oh, let's bring in data scientists. Let's hire tons of data scientists. Well, they're actually quite hard to find. This is a skill set that's and it's quite a lucrative skill set. So a lot of people that are professional data scientists, it's hard to recruit them into our domain. So the key here is to teach people how to code, to give them the tools to automate processes, to work with larger data sets, to give their toolbox a much kind of a boost, which allows them to do lots of things that they couldn't already do, and really drive towards what's called the hybrid skill set that's needed to differentiate themselves in the job market, essentially. And this is probably something that in your guys's institute you've probably seen, is that people coming out of the programs, maybe as master students or even undergrads or even PhDs, with these skill sets are able to come into companies, into jobs that didn't really exist before. They're basically creating new jobs because of this hybrid skill set that they have. And that's really exciting and interesting that we're on that forefront. But this is nothing new. This is something that's happened in all of those industries I mentioned before that have been innovated or disrupted upon. Is in the very beginning, they also had this like initial curve of people learning to code coming into their industries. So in NUS here in Singapore, there's a couple modules that I've created, a couple teaching modules. One of them is called digital construction. The other is called data science for the built environment. And these are similar to what you would learn in computer science or data science, but in this specific context of buildings, of the design, construction, and operations phases of buildings. And this is really powerful for people, because if you, like maybe some of you have done this, you've taken classes in computer science or even data science, which is supposed to be more applied, and you learn how to process Twitter data, or you learn how to recognize pictures of dogs versus cats, right? These are all very generic examples because they have to be. But to really motivate people, I found that is if you start allowing them to practice and learn data science in areas that they really care about, because it's part of their job or their trajectory, the motivation becomes much higher when you put it in their context. So these two classes were great because I got to reach lots of students in NUS. But what about the rest of the world? There's lots of online courses like Python for everybody and Python for data science that you can learn Python and other tools. But these are, once again, these are generic. So about 2 years ago, I got started on the process of creating a data science course, one of the first of its kind that tries to directly go into a certain general field. In this case, it's broad and well, so I chose construction, architecture, and engineering, which is already a bit too broad. In this course, you can check it out. Obviously, that's why I bring it up, because if you're interested, you can check it out. If you already have coding skills, you might be more advanced than this course. What I try to do in this course is get people started with Python, but also with certain libraries like pandas or scikit-learn or matplotlib or seaborn, or really basically practical libraries, but always applying it to different contexts from the built environment, but not usually going super deep into any certain specific context, because I wanted it to be broad enough to try to capture that. The community. This is very different than most programming classes. Most programming classes, you start very slowly and then you build your way into application. In this course, it's the opposite. You dive headfirst into some pretty moderately advanced data sets, and you learn how to analyze those data sets before you learn perfectly what all of the Python objects and all the pandas functions actually do. So I often recommend for people to take this course alongside a more generic Python course to try to round those things out. But overall, the feedback has been great. People have really felt like it helps motivate them. There's been about 15,000 people sign up in 2020 to take the course, which actually is quite good for such a kind of what they call a niche edX course, which is in a specific area. The demographics are usually people that are in their late 20s, early 30s, usually people that have degrees. They basically have worked maybe a few years in the field, and they want to try to diversify or hybridize their skill sets. And lots of people from all across the world, once again, sort of like getting people from all corners of the globe. In this case, for this course, US, India, and Singapore turn out to be the most popular. But we're looking at growing that. And then, of course, like I said, the feedback. So I've gotten tons of feedback from people in all different corners of the building industry, sort of really happy that somebody's paying attention to the context and the application. I'm planning to renovate this edX course to try to make it even more effective, despite the width of the course, the breadth of the course across design, construction, and operations. The design part of this course is not as developed as what, you know, the type of things that you all probably do in your institute. But if anyone in this group is interested in learning more about online courses and how to make them, please let me know, reach out to me, because I would love to see a much better or more detailed or more focused edX course that maybe the ETH would be, somebody from the ETH would be interested in making. Because it's really rewarding. I have a lot of tips on how to make it manageable. Making a big online course might sound very daunting, but I've figured out ways to make it a more manageable process. So thank you so much. I hope we have, I think there's about 10 minutes left. So, but we got started a little bit, so maybe we get a little time over 6 o'clock to answer questions, but I would love to take any questions at this time.
Thanks again, Clayton, for the nice presentation. A very interesting discussion also. I really enjoyed it. And yeah, finally, I cannot comment on an upcoming talk yet so far, but the whole team of Design++ initiative wishes you a wonderful Christmas and a happy new year. And we will be back in January 21 with new talks and let you know about this in due time. Thanks for the attention.